Thank you. Thank you for the invitation. I'm very happy to be here and to have this kind of joint workshops. So I'll talk today about detection and attribution. This falls into the first part, what Lynn presented. It's more on the climate science side. Okay, so this is joint work with Sebastian Sippel, Reto Knutti, and Erich Fischer on the domain science side from the Institute for Atmospheric and Climate Science at ETH Zürich, and more on the machine learning statistics side. It's Nikolai Meishausen from the Seminar for Statistics at ETH Zürich and Guillaume Bozinski from the Swiss Data Science Center. Okay, so just to present briefly the climate system. The Earth is a very complex system with a lot of nonlinear feedbacks. Some of the feedbacks and interactions are known, but not all of them. And all this is very coupled between the different components of the climate, and there are four main components for the climate: is the atmosphere, the oceans, the land, and the ice. And we can think of the climate system as a system that has some variability that is internal. It's natural. It's also called unforced climate variability. But then also from the outside, there are some drivers that are influencing the variability in the climate. And there are two main external forces or drivers, and those are the anthropogenic forcing and the natural forcing. And by natural forcing, I mean it's mostly the sun and the volcanoes. So we have internal natural unforced variability, and then we have forced variability. And the question is, if we frame this as a signal versus noise problem, the question is, if we consider the internal variability as the noise in the system, can we extract some signal out of the data, a signal that comes from these external drivers? So that's the main question that we are trying to address here. And sometimes the problem that happens is that we know on long term what happens on the decadal or annual. We see the trend. That's easy to see it in the noise. But then if we look at different scales, both spatially and temporal, for example, daily or regionally, then the internal variability gets larger, the noise is larger, and the question, can we see the signal in there? Or are we like kind of not seeing it because the noise is too large? So there are open questions, in addition to the physical understanding that we have of the climate system. Part of the climate science, there is a subfield called detection and attribution. And what detection and attribution tries to find is the causal links between these external drivers of the climate system and the changes that we are seeing, for example, in temperature or humidity or precipitation. And if we break it into the two parts, detection looks to see if there is an externally forced climate change that cannot be only explained by internal variability alone. And here by climate change, I just want to stress that usually while in the media it's used like human-induced global warming, here climate change is any change that is due to any of the external forcings. And then if we detect a change, the next question is what can we attribute it to? To one of these forcings or a combination of forcings. How detection and attribution works, so this is a field that has been very active in the last 30, 40 years. And I'll just present on this slide how traditionally detection and attribution works. What happens with these climate simulations is that because we have the physical model, the equations of motion, the PDEs, this allows us to run the climate simulations with the forcings that we want to. For example, the blue line here, it's a model simulation only with natural forcing. This means only volcanoes, which are these dips, and the solar activity. Then the red one, it's a climate simulation only with anthropogenic forcing. And I know it's not very visible, but there is a gray one, which is the sum of the two. And then we have in black, we have the observations. So what traditional detection and attribution tries to do is to explain the observations, let's say temperature, as a function of these different climate simulations to which we have some internal variability, which is the noise. One thing that happens is that because these observations are high dimensional, it's very hard to do the regression in this high dimensional space. So the first step that is done in detection and attribution is to reduce the dimensionality. using some unsupervised technique. Usually in climate science, it's empirical orthogonal functions, EOFs, which is similar in machine learning to principal component analysis. And then the regression is done in this reduced space. And the magnitude of the coefficients will actually tell us how much of the change in the observations is explained by each of these climate simulations. So if we would have a very large alpha ant and a small alpha nat, this will tell us that most of the observations are explained by the anthropogenic forcing. We know that PCA or EOFs maximize the variance, so we can think of this being unsupervised. It remains arbitrary to a certain extent, and then we could use different dimension reduction techniques. There is a multitude in machine learning, and then who knows what, I mean, the reduced space will be different, of course. So what we are actually proposing is so in these model simulations, we have the forcing that is actually driving the simulation. So we have the information on the forcing. So the question now is, if we have this information, can we use it in a supervised way to, instead of extracting the fingerprint in an unsupervised way, to extract the fingerprint in a supervised way? So again, we have the same setup. We have a climate variable that can be temperature, humidity, precipitation, and so on. And then we have an external forcing, can be anthropogenic, solar, volcanic, and so on. And then we can write an optimization problem where we have a loss function, L, that tries to explain the forcing, Y, as a function of the observations. And here F beta can be any regression function, can be a linear function, can be nonlinear kernel methods, can be a neural network, but ideally we want something that is as interpretable as possible. And one thing to notice is that this optimization problem is solved for the distribution P that we see at training time. And we will see that this can pose some problems that we will discuss later. And when we have a new observation, we use the beta, the fingerprint that we had estimated, and we find the predicted forcing. And the way we define detection and attribution in this supervised setting is that we use the predicted forcing as a test statistic for frame it as hypothesis testing. And that's also, I just want to say why it's the name direct, because we extract the fingerprint by predicting directly Y from X, while in the traditional detection and attribution, they don't use Y at all. So in this framework, how do we define detection and attribution? We define a null hypothesis saying that there is no externally forced climate change. And we want to see if we want to reject or accept this hypothesis. And a little bit more quantitatively, how this is done is that we can we can look only at simulations with only internal variability. This will give us a probability distribution, and then we compare the new observations with this probability distribution, and we will see if this is distinguishable or not from internal variability, which is almost equivalent saying if it's zero because there is no signal. We said the signal is the external forcing. And to do attribution, we say, let's say we want to predict the anthropogenic forcing. If the true forcing Y lies within the confidence intervals of the predicted forcing, then we say that we can attribute the change to that forcing. And I'll give an example of each of them in the following. Okay, for detection, first thing that we did is that we can, for example, if we look at every location on the Earth locally, and we do plot the distribution of the local daily temperature anomalies for 2 time intervals, 1951 to 1980 and 2009 to 2018, we see that the distributions overlap significantly. And they also have a very large variability. So it would be very difficult in this case to say if the 2 distributions are different or not. Okay, just to say another thing is that until now there was a lot of work on detection and attribution for annual scales or larger time scales. While here our question is, can we see a signal in the daily data? And then we can do exactly the same thing, but taking the global daily temperature anomalies, so as an average over the whole globe, and then we see that for the same time intervals, the two distributions barely overlap. So this starts to help us see that maybe there is a signal in the data. How this works in practice is that, again, we have our climate system with some internal variability. And in the first step, we extract this fingerprint, as I said, in a supervised way. We extract beta hat, in which we predict some metric from the, let's say, temperature data. In the next step, we have our climate simulations only with internal variability. We project these simulations, which are spatial pattern, onto the fingerprint that we learned here, and then we get a predicted forcing, which is a one-dimensional vector, it's a scalar. And then taking all these values will give us some distribution. And this is the distribution of the data coming only from internal variability, which means there is no external forcing explaining our observations. And next, what we do when we have a new observation coming in from real data, we can do exactly the same step. We project them on the same fingerprint. We get an estimated forcing, and now we can compare our predicted forcing with our distribution. Is this predicted forcing within the distribution or not? If it is within, we cannot say that we have detected a change, while if it's not, we can say we detected a change. And so our question, as I said, was if we look at shorter time scales, for example, daily, and looking at a global pattern, can we say something if there is an externally forced climate change or not? And this work was published beginning of January this year in Nature Climate Change. And what we found is that if this is the distribution only from internal variability, so there is no external forcing, we do the same prediction as I showed, and this is from around 1850s to nowadays. And then we see that starting around 2000, most of the points fall outside of this distribution. There are still some points that fall within, but then starting in spring 2012, every single day falls outside of this distribution. So we see in daily data, if we look at a global spatial pattern, that every single day now falls outside of this distribution, so there is some externally forced climate change. And if we look at yearly data, we can see it starting in 1999, where every year falls outside of the distribution. And we did the same analysis, but by taking the trend out, which the trend makes the prediction easier. And so now the prediction only relies on the spatial pattern. And we see that the prediction is a little bit more noisy, but also again, starting around 2012, every single day falls outside of this distribution. So if we want to start really seeing if there is a climate change, because locally there is a large internal variability, we need to start to look globally if we wanted to see something on shorter timescales. And now I'll move to attribution. If we consider that our climate variable x is influenced by different external forcings that all have a causal effect on x, let's say this is the solar forcing, this is the volcanic forcing, and this is the anthropogenic forcing, and we want to predict F3, which is the anthropogenic forcing. We want to predict F3. We want to learn beta. And what happens is that if we learn the prediction only using X and F3, and if there is a change in F1 or F2, because they have a causal effect on X, this might make that the prediction doesn't work well anymore. And our goal is to, even if there is a change in this F1 or F2, we want that our prediction works well, even under this, what we call distributional changes. And if we recall the initial optimization problem, it was optimizing only over the distribution P that we see at training time. But if at testing, the distribution comes from an out-of-distribution sample, then we have no guarantee that the prediction will work well. So the goal is to rewrite this optimization problem such that it takes into account these shift interventions. So shift interventions comes from the causal inference literature, and they shift the value of a variable by some value. And now we can rewrite the optimization function not only over P, but over a whole class of distributions Q that come from these shift interventions. And this is, it's as if solving an optimization problem in a worst case scenario. What this guarantees is that if there is a change in the distribution that comes from changes in F1 and F2, the prediction would still work well. So this is our goal. We want to achieve distributional robustness. We want to be robust to these changes in the distribution. And for example, if we want to predict Y, which is F3, we can consider as anchors all the other external forcings, for example, F1 and F2. And to implement this distributional robustness, we use a newly introduced method last year by Rottenhäusler and co-authors called anchor regression. And this is the estimator. And we see that the second term looks like a regularization term. What it does is that it projects the residuals onto the space spanned by this anchor. And what it says is that by increasing this gamma, which is called causal regularization parameter, by increasing gamma is that we give more weight to this term, which means that when we project the residual onto this space spanned by the anchor, we want to have a slow a value as possible. And in a way, what this does is that when we increase gamma significantly, this encourages the orthogonality of the residuals with the anchor. And just to show that this is a generalization of other regression cost functions. For example, when gamma equal to 1, this is ordinary least squares. And when gamma goes to infinity, this is the instrumental variables from the causal inference literature, which tells us that by increasing gamma significantly, we go towards a fully causal setting. And in our case, fully causal settings are quite difficult to deal with. So we will use gamma somewhere between 1 and infinity. How does this look like in practice? I show 3 examples for 3 different values of gamma. On the first row, it's gamma equal to 1. Here it's gamma equal to 100. And here it's gamma equal to 10,000. And first thing to notice when we look at the root mean square error is that by being robust, we lose a little bit in the prediction accuracy. And RMSE goes from 0.22 to 0.27. So we lose a little bit in prediction accuracy, but we gain in robustness. And then also, if we look at the correlation, so I said we want residuals which are uncorrelated with the anchor. So now if we plot the residuals versus the anchor, in this case it's the volcanic anchor, the correlation goes from -0.1 to -0.4, so it goes down. And in terms of spatial patterns, one thing that we see is that most red is positive, so most of the coefficients are positive, which means that most of the locations on the Earth contribute to explain the anthropogenic forcing. And as we increase gamma, as we protect ourselves against the volcanic anchor, we start to see some negative coefficients. So how we interpret them is that it might make us believe that these areas do not contribute to explain the anthropogenic forcing, but that is not the case because we know from here that they do. What it does is that it tries to find those predictors, those locations on the Earth that explain the anthropogenic forcing, but do not explain the volcanic anchor. So the whole point of this is that in the future, we might have some changes in all these other forcing that are causing the changes in temperature, and we want to protect ourselves against such changes. And in this setting, we can do attribution. For example, the black line is the true forcing, is the anthropogenic forcing. And the red one is what we predict, with the green, the confidence intervals. And we do attribution, so if the true forcing, the black line, falls within the confidence intervals of the prediction, then we can attribute the detected change to the respective forcing. And just here, I didn't mention, I didn't have time to introduce the data, but we use data from 1870 to the end of the century, which are projections. Okay, to summarize, we introduced a novel statistical learning technique for detection and attribution, and this falls into the framework of supervised techniques. That's why we call it a direct approach. In terms of daily detection, we can now detect that there is an externally forced climate change for every single day since 2012. if we look at the global spatial pattern. And distributional robustness, if we want to do attribution, it's important because it protects us against future changes in other external forcings that have a causal influence on the data. And one of the implications of this, for example, of the daily detection, is that up to now we said weather is not climate and the hurricane cannot be influenced by climate change, but now with this thing we can try to maybe make connections between for extreme event attribution. And thank you.
Thank you very much, Eniko. Questions?
Hi, thanks very much for the talk. I was struck by the graph that you showed of the local versus the global one, because I was always taught that the local effects of climate change are not equally distributed across the Earth. So I was kind of wondering where this is actually located and to what extent that is sort of representative of the local image.
So this is for every location on the Earth if we take the seasonal cycle out. So we take the anomaly for every month separately, but for every location on the Earth, every grid point.
Hey, great talk. Thank you very much. Yeah. So having had some experience in modeling chaotic systems, what I've always noticed is we are really good at describing what has happened already before based on our observations, but we find it extremely difficult to forecast what's going to come, right? Have there been any longitudinal studies that you're aware of that actually follow our capability to forecast accurately in the climate change area?
So this work, it's not forecasting, it's nowcasting. I think there are more and more people, for example, who are trying to compare forecasting using deep learning with a forecast from a dynamical system, let's say of something like ENSO. One of the things is that here the anthropogenic forcing is fairly linearly correlated with the temperature, so that's, I would say, the easier problem. If we look at the water cycle, like precipitation or humidity or moisture, evapotranspirations, all these are a little bit more complicated. So while there are problems like temperature anthropogenic forcing, which are easier to predict, there are others that are more difficult. Yeah.
Thank you.
I was curious, how do you represent the anthropogenic forcing function? Is it like a local function or a global function?
The anthropogenic forcing is a one-dimensional vector. It's one value per globe. It's one value for the whole Earth. So it's not local, it's global.
Thank you for the talk. It seems you built a very interesting tool to do the monitoring and to observe the behavior of the global climate. Do you plan to make it public?
Which part you mean?
The detector.
This is in this paper. Mm-hmm. Everything is in this paper.
Correct. If I understand correctly, so you're saying that every day you can run the model mm-hmm. and to show what is changing. So mm-hmm. You can see how good is your model, and you also can see what's the effects. Can other people see it?
You mean like for making the code available, or you want to run it
like
with your own data? Yeah, all the code is available. It's at the end of the paper.
Okay, thank you.
So this is just for detection. And for attribution, we have a small workshop paper, but we are working on, and we will make, this is the second one, we will make everything available as soon as we have it clear. But detection is in the first paper, the code is available on the data. Some data, not everything is possible.
Let's thank again Eniko.